Hi children, we'll move on with our problem section. Today we'll cover two chapters. One is dual nature of radiation and matter, the other one is atoms. Actually, problems in these areas, especially modern physics, relatively easier compared to the first volume chapters. So, if you prepare thoroughly, definitely will attend one problem in your board examination. So, in the direction, I've chosen some problems. First one, in dual nature of radiation. Let's read the first one. Very easy. I'll read. A 60 watt bulb emits photons of wavelength 550 nanometer. 60 watt bulb. Calculate number of photons per second. If this source of light is threshold wavelength, find its work function. Now, students, according to our quantum theory of radiation, the quantum theory of radiation, energy emitted in the form of packet of energy per photon, if I denote energy E, h nu. Since wavelength is given, h Planck's constant, nu frequency, how do you write? hc by lambda, according to quantum theory of radiation, or generally for a wave, speed of wave is f lambda, or for frequency f, we write speed divided by lambda. For electromagnetic waves, we use nu instead of f and c instead of v. So, this is the expression. Now, what he has given in this? In this, he gives two important datum. One is power emitted. It sends out energy per second, that is 60 watt. 60, what is watt? Joule per second. And wavelength of light emitted. What is wavelength of light emitted? 550 nanometer. 550 nano 10 to the power minus 9 meter. That's it. Now, we have to continue this way. Solution is very simple. Let energy emitted per second from source B U is the energy emitted per second in 1 second, and n number of photons per second. You think this way. Actually, what you have learnt in this chapter, see, light is emitted not continuously as a wave, but in the form of packet of energy. Value of each packet is h nu. There are n such packets making up an energy u. Right? Like a total energy, u is collection of energies of each photon, h nu. Each photon energy is h nu. How many are there? N such. So, energy of each photon into total number of photons is total energy emitted. That's it. Very simple logic. You have learned it several times. This is one, you think this way. But by definition, last year you learnt about power. What is power? Power is work per time or energy emitted per unit time. So, if I substitute for u, his energy per second is power, because he is given power. When power is given, use this formula: total energy emitted per unit time. What is total energy? Energy per photon into number of photons. You get by heart these relations. Every time they ask this way, power ant kodtidda hagene, you think energy emitted per second is power. Per second means unit time. Energy is collection of energies of sum of the energies of photons. There are n such photons per second. So, total energy is nh nu divided by t. This is the relation. If they ask time, you solve for time. If they ask power, solve for power. If they ask n, solve for n. If they ask nu, solve for nu. Remaining will be given. Here, except n, everything is given. Therefore, you solve for n. You are supposed to find n here. So, it is pt divided by h nu. Just to remember this. If you remember these key steps, then whatever the changes going to make, you can easily notice, identify and solve. Very simple. What is P60 joule SI? And per second means time, 1 second. Divided by what is Planck's constant? 6.625 10 to the power minus 34. Even if this is not given in the problem, use this value. You are very much familiar with this Planck's constant. And the value of nu frequency, has it been given? No. Before I make a substitution, I'll remove this. I'll make substitution afterwards. Has it been given on the data in terms of frequency? No. Wavelength is given. According to our wave theory, use this C by lambda. So, you make another substitution, Pt divided by h into C by lambda. Lambda comes to numerator. Pt lambda divided by hc. H and C are universal constants. You know the values of the constants. Put the values. P60 1 into lambda 550 nano 10 to the power minus 9 divided by h Planck's constant 6.625 10 to the power minus 34 into speed of light 3 10 to the power 8. So the value, I'll find it, and s. The value 1660.4 10 power 17, or n that equal to 1.66 10 raised to the power, shifted by 3 places, 20 photons, just numbers, per second. In 1 second, how many? As many as 1.66 10 power 20. Just remember this up. Power equal to total energy by time. Energy in terms of number of photons, nh nu, where h nu, energy of each photon, n total number of photons. That's it. And c, nu, c by lambda. These things you need to remember. And h 6.625 10 power minus 34. Planck's constant, if not mentioned or given in the problem, use it. Planck's constant. And work function you have to find. What's work function? Work function, second one. What is work function? The minimum amount of energy required just to remove an electron by the photon. Photon having energy h nu. If nu is the threshold frequency. What is work function? H nu naught. H times, what is nu? C by lambda naught. If wavelength is given. Here in this problem, take lambda incident value itself as lambda naught. What is that? 550 nano 10 power minus. That's what he says. So rest is very simple. H 6.625 10 to the power minus 34. You get it by heart, these values. What is C? Speed of light, 3 10 power 8 meter per second divided by the value of wavelength 550 10 to the power minus 19, and the value will be in joule. I write it first, and if they ask, you have to do it in SL. And this power, you make it a small correction. 6.62 10 to the minus 34, 3 10 to the power 8 divided by 550 10 to the power minus 9. That's equal to 0.036 10 to the power minus 17. If you want it in EV, divide by 1.6 10 to the power minus 19, because 1 EV is 1.6 10 power minus 19 joule. This part That's why you divide this value by 1.6 10 power minus 19. So the value is 2.25 EV. It's very, very simple. Now we'll move on with this almost similar approach. Second one, radiation of wavelength 450 nanometer is incident on a photosensitive metal having threshold wavelength 600 nanometer. See, wavelength of incident ray 450, threshold wavelength 600. Find the maximum kinetic energy of the emitted photoelectrons. Remember students, always in all the problems in this chapter and also coming chapters, the values of universal constant, even if not mentioned, you use like Planck's constant 6.625 10 power minus 34. It is actually given along with the problem in the exams. I am not given here, it will be given joule second. The value of speed of light 3 10 to the power 8 meter per second. Okay. Now we'll write given. What is given here? Solution part. Solution. What you have to find? Kinetic energy. Hint is Einstein's photoelectric equation. What is PE? Photoelectric equation. That is incident energy h nu that equal to work function times kinetic energy K. This is Einstein's photoelectric equation. What is work function? H nu naught plus K. If the data provided in terms of frequency, use this. But here in this problem, they have given frequency in terms of wavelength. So for wavelength frequency, you make a substitution C by lambda. And nu naught, hc by lambda naught plus K, where K is kinetic energy. Okay. We'll continue. Now you solve for K. He wants you to find maximum kinetic energy. How do you do? Bring it to left side. I write K first. That's why on one side. Hc by lambda minus hc by lambda naught. So hc is a constant. You take it outside. C, small c, speed of light. So 1 by lambda minus 1 by lambda naught. So K that equal to hc times, what's lambda? Lambda naught, denominator LCM, lambda naught minus lambda, that's it. Now you put the values K, kinetic energy, the value of H, Planck's constant 6.625 10 to the power minus 34 into C 3 10 to the power 8, right? And that equal into bracket, what is lambda naught? Lambda naught is 550 600 nanometer minus 450 nanometers, where 450 divided by 600 into 450. Now you take nanometer outside the bracket, nanometer. Here is common, nanometer taken common. But here denominator, since you multiply the two, there are 2 nanometer terms into nanometer. So 1 cancels. The other one comes outside, 6.625 into 3 into power 10 to the power minus 26. And here 150 divided by 600 plus into 450 times nano, denominator 1 by 10 power minus 9. Now you simplify the value, you will get, okay students, if you multiply these two and multiply this and also divide by these terms, you'll get 0.01104 10 power minus 17. Do it once again, do it yourself, right? It's 450 nanometer, correct? 450 nanometer. Now in EV, if you write in EV, it's not asked, he is not asking whether to write final answer in Joule or EV. You do it in both Joule and EV. Practice this in EV. How do you find it in EV? K 0.01104 10 to the power minus 17 whole divided by. To write in EV, as I told you, like a previous problem, divide by 1.6 10 power minus 19. If you do, you will get a value around 0.69. What's the unit now? EV. You can write either in EV, say that it's 0.69, or in Joule 0.01104 10 power minus 17. This is the question. Now we'll move on, students. One more. What is that? The work function of cesium metal is 2.4 eV. When a light of frequency, I'll write frequency, some value 4.5 10 raised to power 14 hertz. Let's use this value. Is giving frequency of incident radiation, not wavelength this time. Is incident on a metal surface, photo emission occurs, find energy of incident photons, maximum kinetic energy of photoelectrons emitted. Work function already given in terms of EV is giving the work function directly. In the previous problems, what did we do? We found work function using the formula W H nu naught if nu naught is given, or Hc by lambda naught if lambda naught, threshold wavelength, is given. But here he gives directly omega work function. So let's list out given. He gives the value work function in EV 2.4 EV. You have to write kinetic energy of photoelectrons. If you retain EV only, you have to write incident energy in EV and express final answer also in EV. Or else if you want to write in joule, you can do it in joule. If you want it in joule, what work function, what do you do? 2.4 into, what's 1 EV? 1 EV, 1.6 10 power minus 19. Now it is in joule. You can multiply these two and write the answer as 3.84 10 to the power minus 19 joule. You can use for W 3.84 10 to the power minus 19 joule or 2.4 EV. And I use incident frequency nu 4.5 10 to the power 14 hertz. It's very simple. Now the first part, what's that? Energy of the incident photon. Energy of incident photon. How do you find energy of incident photon? E that equal to h nu. It gives nu directly. H value 6.625. As I told you, assume this value a constant minus 34 into the value of frequency 4.5 10 raised to the power 14 hertz. So the answer is E. You multiply the two, 6.625 into 4.5. You are getting the value around 29.8125 into 10 raised to the power minus 20. Or if I write 10 power minus 19 to express in EV, because power of EV 10 power minus in terms of joule. That's why if I shift one place to the left here, I get 2.98, almost 3, 10 to the power minus 19. Let us retain this only, decimal places, 2 places after decimal point. Final answer will round it off. Now it is in joule. In EV, if you want in EV, or if it is asked to express the value of energy incident in EV, what do you do? Same procedure, routine. Divide the value by 1.6 10 power minus 19. If you do, you will get a value 1.6. So, you are getting value around 1.86 EV. See, incident energy 2.4 and incident energy 1.8, work function 2.4. Second one, you have to find maximum kinetic energy of the photoelectrons. Maximum kinetic energy of photoelectrons. What do you do? For this, you will use Einstein's photoelectric equation, that is incident energy h nu that equal to work function plus kinetic energy. You solve for kinetic energy here. This implies incident energy E that equal to h nu that equal to W plus K. You solve for K. What is K? E is h nu actually. You have found h nu minus W. What is E? 1.86 minus what is W? 2.4. So it's 1.86 minus 2.4 and that equal to minus 0.54 EV. Energy is in EV. And another important point you have to observe is kinetic energy is negative, is coming negative. According to our Einstein's postulates and also explanation of Einstein's photoelectric equation, he says kinetic energy can never be zero, right? Because incident energy should be more than work function. So here incident energy coming 1.86. Energy required to emit electrons is 2.4. So the energy incident is less than the energy required. So no emission is possible then. That's why kinetic energy negative implies. Kinetic energy negative ಅಂದ್ರೆ ಏನು meaning? Emission is not possible. This implies since you just explain this way. Since kinetic energy is negative, photo emission is not possible. You have to write answer this way. I think in this problem, they have chosen this value 4.5 10 power 14 hertz wrongly. Frequency should be more than this, maybe 5, 15, 10 power 15 hertz, something like that. But if they have chosen purposefully, they want you to answer this way finally. Since kinetic energy is negative, photo emission not possible. What is the meaning of this? Energy required is 2.4. Incident energy is 1.86. No emission. So you have to solve this way. Don't stop half the way saying, kinetic energy you are getting negative and option data are wrong. You cannot say that. You express answer this way. This is what they may be expecting you to, right? That's why minus 0.54 kinetic energy negative, which is, what is the meaning of this? Emission is not possible. Incident energy is this. Threshold work function is this. So emission not possible. No photoelectric emission in this case. That's what, right? We'll move on with the fourth one. Photon of wavelength 5400 angstrom, you write angstrom, A upon 0 upon E, is incident on a metal surface of threshold wavelength 6100 A over a 0, you write angstrom. So incident wavelength this, threshold wavelength this, 6000 angstrom. Calculate maximum kinetic energy of the photoelectrons, stopping potential, maximum velocity of the emitted photoelectrons. So almost repeat calculation. Now let us list out given what he gives. He gives incident wavelength as 5400 angstrom. What do you write for 5 angstrom 10 power minus 10? 10 power minus 10 you will write that. What is threshold wavelength? Minimum wavelength required to just, maximum wavelength required to just emit an electron, not to move. More energy is provided, it starts moving. Right? One more, what else? That's all. And constants H 6.625 10 to the power minus 34 and C speed of light 3 10 to the power 8 meter per second. These terms you have to use. Now the point is, or the calculation part, first one, what is maximum kinetic energy? Why the word maximum? Out of some n electrons emitted, 1 or 2 will be moving with maximum energy, which were possessing maximum energy when inside the metal, before emission. You have learnt about that. What is this? You have to now use Einstein's photoelectric equation. EPP means short form Einstein's photoelectric PE. Photoelectric equation. PE. What is that? That is incident energy H nu, that equal to work function plus K kinetic energy. K max you write. So you solve for K max, maximum kinetic energy. Only few electrons will move with maximum, remaining electrons less than that. H nu minus W. You know W, what is W? H nu naught. Here the wavelengths are given, not frequency. So what do you write for wavelength frequency? You make a substitution C by lambda. That's what we did in the previous problem, lambda naught. Now you solve for K maximum this way, HC a common factor, and you take LCM and solve. What did you do in the previous problem? Lambda naught minus lambda. Put the values 6.625 10 to the power minus 34 into, I think space is not sufficient enough. So I'll write here below. K maximum, that is 6.625 10 to the power minus 34 into 3 10 to the power 8. And here the term lambda naught 6100 angstrom minus 5400 angstrom. I take angstrom common outside the bracket. So 6100 into 5400, 1 angstrom numerator, 2 angstroms denominator. So 1 angstrom cancels. So you're left with K maximum that equal to 6.625 into 3 into this difference 0, 0, 11 minus 4, 7 and 0, that's a 700 divided by 6100 into 5400 denominator term. That's it. Into power 10 to the power minus 34 plus 8 and this denominator 10 to the power minus 10 is angstrom. So if you do simplification, this is the value, students. If I do the simplification, try it out once, you are getting the value K maximum that equal to 4.224 10 to the power minus 20 joule. This is the value in joule. Right? You can write in EV. If I write in EV, divide by 1.6 10 power minus 19. Second one is stopping potential. We have to find stopping potential. What is stopping potential according to our Einstein's photoelectric equation? Also experimental observation. Stopping potential in the experiment. What did we do? We applied a negative potential to anode. For a particular maximum value of negative potential, all the electrons, even most energetic electron, will be completely stopped from reaching the anode, and that value of voltage, negative voltage applied to anode to stop electrons is stopping potential. How do you find stopping potential? By definition of PD. What is potential difference? Work divided by charge. What is work done? Work done equal to here kinetic energy divided by charge, because here in the photoelectric effect, work is done to stop the electrons, means neutralize the kinetic energy. Work done equal to kinetic energy. That's why if I denote stopping potential by V, 0, stopping potential, kinetic energy already K maximum we have written, divided by charge E, because electron, that's why charge. So what is K? K stopping potential, because you remember this relation, that is relation is kinetic energy maximum that equal to EV naught. That's all. This formula, you remember it as a formula now. Kinetic energy maximum is EV naught. Like work that equal to charge into potential, or charge into potential difference, second chapter. From this relation, work done is kinetic energy, charge is electronic charge, and the potential difference applied between anode and cathode to stop the electrons is stopping potential. Continue. So V naught, what is K? 4.224 10 to the power minus 20 divided by the value of E, electronic charge 1.6 10 power minus 19. So this is nothing but, finding stopping potential is nothing but expressing kinetic energy in terms of EV. That's it. If we express kinetic energy in EV, that itself is stopping potential. Stopping potential, right? Into 10 to the power minus 1, or V naught that equal to, if you multiply minus 1, 0.264 volts, 0.264 volts. This is stopping potential. And third one, you have to find here the maximum velocity of the electrons, V maximum. To find V maximum velocity, corresponding kinetic energy expression value we have to use. Now use the relation. Kinetic energy maximum that equal to half mv maximum squared. You solve for V maximum square. What's that? 2 times kinetic energy maximum divided by m. You solve for V maximum, that is square root of 2 times kinetic energy maximum divided by m. So V maximum that equal to root of, what is 2 times kinetic energy? Kinetic energy. Now write in joule, which are found in joule here, 4.2 to 10 power minus 20, not that in EV, because SI unit. So it's 4.2 to 4 10 to the power minus 20 divided by mass of the electron. What's mass of the electron? It is also universal constant, which can use directly even if not given in the data, you just directly use it, minus 31. So the value of the term in the bracket is, students, if you substitute and solve, multiply, you get 0.0928 10 power 11. While finding root, you have to make power of 10 an even number. It's an odd number 11. How do you make it? Multiply 110, take out of 11 tens 110 and multiply with 0.9284. We get 9.284 10 power 10. Now 10 power 10 comes outside, becomes 10 power 5, and root of 9.284 is 3.05, nearly 10 power 5 meters. This is the maximum kinetic energy. Maximum kinetic energy of emitted photoelectrons 3.05 10 power 5. Threshold, stopping potential 0.264 volts. What is this? This is the voltage to be applied to stop the photoelectrons from reaching the anode. How do you do it? Kinetic energy maximum is EV0, where V0 is the stopping potential, E, charge of the electron. If we express this kinetic energy in EV, that itself is stopping potential. Remember this. We will use it whenever required. We'll move on with another one, slight difference. When the wavelength of radiation incident on a metal surface is increased from 410 nanometer to 620 nanometer, the maximum kinetic energy of photoelectrons found to decrease from 2.63 eV to 1.6 eV. Calculate the value of Planck's constant. So we will list out the given, students, here. Wavelength of radiation initially 410 nanometer, right? 410 nanometer. That is in our calculation here 410 nanometer. It is increased to 620 nanometer. Remember, if wavelength increases, energy of the photons decreases. That's why, see, when incident wavelength 410, kinetic energy is 2.63. When incident wavelength is 620, kinetic energy 1.6. So let us list out given. Lambda 1 wavelength 410 nanometer. What do you write for nano 10 power minus 9 meter? When kinetic energy K1 is 2.63 EV. EV, you write. Next case, lambda 2, 620 nanometer, 10 power minus 9 meter, when kinetic energy of the emitted photoelectrons is 1.6 EV. We have to write that EV in electron volt. We will do it after the substitution. How do you do it in joule EV? 1 into 1.6 10 power minus 19, that we will do. Now, the required formula to be used in this calculation, can you guess? As Einstein's photoelectric equation, that is incident energy h nu, work function h nu naught, plus kinetic energy k, k in my discussion is k. Okay. For incident wavelength, it is given frequency wavelength, that's why you write this in terms of wavelength c by lambda, that equal to hc by lambda naught plus k. So first case, k is 1. There are two cases, wavelength lambda 1, wavelength lambda 2. Case 2. So hc by lambda 1, that equal to hc by lambda naught plus k1. And case 2 for the second wavelength, students, hc by lambda 2, that equal to hc by lambda naught plus k2. And here you don't write lambda naught 1, lambda naught 2, because lambda is a constant. Lambda naught constant for a metal. One metal, work function, threshold frequency, threshold wavelength, constants. Now, if you subtract 1 by 2, you do subtraction this way. Kinetic energy K1 more, that's why you do simply subtraction like this. hc by lambda 1 minus hc by lambda 2. What are you doing? You may take this equation number 1 and this equation number 2. What are you doing here? Equation number 1 minus equation number 2. First you subtract left hand sides. So right hand side term, this cancels. That's why kinetic energy K1 minus kinetic energy K2. That's it. Now you take hc outside. You are left with 1 by lambda 1 minus 1 by lambda 2. And that is equal to K1 minus K2. You have H here. You have to find Planck's constant. So take LCM lambda 1, lambda 2, lambda 2 minus lambda 1. That is equal to K1 minus K2. Yes. What you have to find? He has given lambda 1, lambda 2, K1, K2. You have to find the value of H. You know value of Planck's constant. But in this problem, we have to find it out. For these two values of wavelengths and corresponding kinetic energies, calculate Planck's constant. That's it. Now, how do you do further? You can try this way. H, you return the left side. You send this to right side. So it becomes lambda 1, lambda 2 numerator divided by C denominator, lambda 2 minus lambda 1 into K1 minus K2. Now you make a substitution, right? Yes. What is lambda 1? Lambda 1 is 620, 410 nanometer. 410 nanometer into 620 nanometer. There are 2 nanometers into nanometer. We will cancel it out. One term. So speed of light is 3 10 power 8. And this 620 minus 410 nanometer. You have taken nanometer outside, common factor. And for kinetic energy, you write 1 is 2.63 minus 1.6 into 1.16 power minus 19. Right, 1.16 power minus 19. 1.6 into 10 power minus 19. Okay, why this term? Because this is in EV, this is also in EV. You convert this EV by multiplying 1.16 power minus 19. For both the terms, you multiply 1.16 power minus 19. That's why it's a common factor. Take it outside. 1 nanometer cancels. So you have on the numerator 410 into 620. And this difference, students, if you subtract this, you get 1.03, and you subtract these two terms, you get 210. The power here, denominator 10 power 8 of velocity, here power 10 power minus 9, minus 19, 1.6 written. If you multiply and divide, you get 6.664.96, 10 power minus 36. Check it out. And if you shift by 2 places, you get finally H 6.6496. If you round it off, 65, 10 to the power minus 34, because you shifted it by 2 places. SI unit is joule second. This is the value. Final answer. That's it. Expression of value of Planck's constant. 6.64 10 power minus 34 joule second is the Planck's constant value, students. It's very simple, straightforward. What you have to think is, work function is a constant for both the cases. That's why work function gets cancelled. So kinetic energy K1 when incident frequency nu1. And that nu you have written C by lambda. So Hc by lambda 1 K1, Hc by lambda 2 K2. If you subtract these two, you get this term and continues. Follow the calculation part, and final answer is this. Practice this, right? We'll continue. Next one. The threshold wavelength of photosensitive metal is 650 nanometer, and wavelength of incident light, you make it light is 390 nanometer. See, threshold wavelength is 650 nanometer. Incident wavelength is 390. Find the maximum kinetic energy. Same procedure, repeat problem. He adds one more to this. What is that? If the wavelength of radiation is increased to 480 nanometer, you make it nanometer. He is increasing decreasing wavelength. No, increasing. Initially 390, now it is 480. If we increase wavelength, kinetic energy decreases. Therefore, find or calculate change in maximum kinetic energy. There are two parts clearly. Let us list out given first. Wavelength initially, this lambda naught 650 nanometer. This is actually threshold wavelength. Initial wavelength lambda 1 incident 390 nanometer. Nano you will make multiply 10 power minus 9. And next wavelength 480 will be increased to 480 nanometer from 390 to 480. That's all. You have to find change kinetic energy. You assume the values of the constants, namely H Planck's constant 6.625 10 to the power minus 34 joule second. It will be given along with the problem. In the problem, given Planck's constant H dash 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 will be given. I am writing that value here. And one more constant, that is speed of light, 3 10 raised to power 8 meter per second. That's it. Now, this is given. First case 1 to find kinetic energy K1, use Einstein's photoelectric equation. Einstein's photoelectric equation, P short form. So that's H nu equal to kinetic energy plus W work function. So it is K plus W H nu naught. So how do you write this? Hc by lambda, that is equal to K plus Hc by lambda naught. So if you solve for K, initially is nu 1, K1, and this is lambda 1, K1. Lambda naught is a constant for both the cases. So I solve for K1, it is Hc, you bring it to left side, and you have done several problems of this type, 1 over lambda 1 minus 1 over lambda naught. What did you do further? Hc times lambda naught minus lambda 1 divided by lambda naught lambda 1. That's it. So the kinetic energy value initially, Planck's constant 6.625 10 to the power minus 34. You do simplifications on your own. 3 10 power 8. And here lambda naught lambda 1. Lambda naught initially 650 threshold minus 390. Nano is there. 650 into 390. Outside, denominator 2 nanometer into nanometer. Numerator 1 nanometer. It cancels. The final value K1 6.625. Do simplification like this in a simple calculator, arithmetic. 6.625 into 3 into, and this value is 0, and 6 5 minus 2 260 numerator divided by 650 into 390 into the power 10 to the power minus 34 plus 8, and this 1 10 power minus 9 nanometer comes numerator becomes plus 9. So the value of K1 is coming around. I have done the calculation per se. You try on your own with your calculator. I am getting the value 0.02038 raised to the power 10 raised to the power minus 17. So the value is 2.038 by 1.6. Because you are doing it in EV. This is in joule. In EV, divide by 1.6 10 power minus, and that's around final value 1.27 EV. Case 2, you will use the same list. What is case 2? For new wavelength, another wavelength. Initial wavelength 390, now it's 480. You start with the same procedure follows. Instead of K1, you write K2, K2 lambda 2. So you start with this formula straight away. K2 HC lambda naught minus lambda 1 by lambda naught lambda 1. So there you write K2 HC lambda naught minus lambda 2 divided by lambda naught lambda 2. You can get it by heart, right? You can use directly. So K2 from Einstein's photoelectric equation you will write, that's why 6.625 all the same 10 power minus 19 into 3 10 raised to power plus 8, and this term in the bracket you write here 480, that's why 650. 650 minus 480 divided by 650 into 480, and numerator into this term here 1 nanometer, denominator 2 nanometers. So the value of K2 finally, you simplify the same way as we did here. So I'll write, yes, my calculator says the value comes around 0.01083 10 power minus 17, and if you shift by 2 places 1.08 10 power minus 19, check it out. In EV, as usual, we will divide by 1.6 10 power minus 19, the answer comes around 0.68 EV. Now the question is change in kinetic energy. So I write change delta K for kinetic energy. Change is final minus initial. Normally we do this way. You can find difference also, but here let's do this final minus initial. 0.68 minus initially kinetic energy 1.27 EV. You have taken EV outside common. So change in kinetic energy minus 1.27 is coming around 0.5 minus 0.59 EV when you round it off. So this implies kinetic energy has decreased due to increase in wavelength. That is the conclusion. There is also one more question. What happens to kinetic energy when wavelength increases? Kinetic energy decreases. Like this, when you solve a problem, you will be exposed to real concepts. You have to think, understand, analyze, and arrive at the answer. That's why your capacity will be enhanced when you solve problems in physics. So practice these steps, students. We'll move on. One more, children, on this chapter. The work function of cesium is 2.14. You write EV is missing. Find the threshold frequency, a simple calculation. Further he says, and wavelength of the incident light. If photocurrent is brought to zero by a stopping potential 0.6 volts. You go to your photoelectric experiments now. In that experiment, there will be anode and a cathode. Cathode emits photoelectrons when radiations fall. Anode collects. When you make anode negative, usually it will be positive to collect electrons. When you make it negative, all the photoelectrons will be completely stopped from reaching anode. That stopping potential difference is called stopping potential, students. That's why now let us list out given what is 2.14 EV work function. First of all, you write that or this value in joule, 1.6 10 power minus 9. Why you want wavelength in SI units, that is meter. That's why you have to write EV in joule. Now it's in joule, right? First part of the calculation is threshold wavelength. Threshold wavelength he wants you to write. Threshold wavelength. Find the threshold frequency. He wants threshold frequency. That's why threshold, I remove this. Threshold frequency. Now which formula are you searching for? S, work function W, H nu naught. So you solve for nu naught. What is nu naught? W divided by H. What is W? In EV converted into joule, 2.14 into 1.6 10 power minus 19. You need not solve this. You can solve finally here. 6.625 10 to the power minus 34. This way you can save time of calculation. So my calculation says answer is 0.5 to 10 power 15 hertz, or if you shift by one place decimal point, 5 power to 10 power 14 hertz. Check this value. Now the second part. What is second part? To find the incident wavelength. Incident wavelength you have to find using stopping potential. His question is, if stopping potential V0 0.6 volts, then what is the wavelength of the incident light? We all know, in the previous problem I told you, stopping potential by using the definition of potential, right? Definition of potential. Yes. What is that? By definition, potential difference is work per unit charge. Work is kinetic energy here, divided by charge, electron charge. So, you want kinetic energy of the electron, so that is EV. Here the potential difference is stopping potential, to stop electrons from reaching the anode completely. So you can solve for kinetic energy in terms of EV naught. Now you can directly use Einstein's photoelectric equation, PE. What is that? That is H nu W plus K. Here H nu C by lambda. You have to find incident wavelength. That's why W you know the value. See here, and W and K EV naught. Right? What is W? Let's write W 2.14 into 1.6 10 power minus 19 plus what is K? K is E 1.6 10 power minus 19 times V naught. What is V naught? 0.6. So Hc by lambda, that equal to 1.6 10 power minus is a common factor. That's why 2.14 plus 0.6 into 1.6 10 power minus 19. You can do calculation in your own way. I'll try this way. This is 2.74. Check it out. Into 1.6 10 power minus 19. You just cross multiply. On the left hand side you have Hc by lambda, right? Now you just cross multiply. Take this to right side and this to denominator. Hc by this value 2.74 into 1.6 10 power minus 19, that equal to lambda. So I'll retain lambda on the left side change ಮಾಡ್ತೀನಿ, and on the right side you make substitution h value. You are writing h value, writing c value. What is h? 6.625 10 to the power minus 34, and the value of c. What is c? 3 10 raised to power 8 whole divided by 2.74 into 1.6 into the power minus 19. So the value of lambda, yes, the value 4.53 10 power minus 7, or it is in meters or in angstrom, 4530 angstrom. That's all. So practice all these types, students. We have covered all the areas of your dual nature of radiation. One question is expected from here. Practice this and be ready for the exam. Now we'll move on into the atom, students. First problem in that. Calculate shortest and longest wavelength of Balmer series of hydrogen atom. Given Rydberg's constant, RB can say 1.097 10 power 7 per meter. Here, solution, the hint. Almost all calculations include wavelength calculation. This relation, wave number number of waves per meter, a reciprocal of wavelength, that is for hydrogen atom, for H atom, 1 over 1 by n1 square minus 1 over n2 square. You get it by heart. For H atom, and you have learned in your hydrogen spectral series, if n1 1, n2 2, 3, 4, 5, etc., the resulting spectral series is called a Lyman series. If electron undergoes transition from 2, 3, 4, 5, etc. orbits to first orbit, spectral series, the radiations emitted during the transition belong to a spectral series called Lyman. If n1 2 second orbit and n2 3, 4, 5, etc. belongs to Balmer series, and n1 3, n2 4, 5, 6, etc. Passion. Similarly, n1 4 bracket n1 5 fun, and n2 higher value than the value of n1. We are familiar with this. We'll continue with the same thing. Now we'll remove this. I have to retain this relation. I remove. Okay, I'll write it again. 1 over n1 square minus 1 over n2 square. Okay, right. Now, the first question, actually, there are two parts. First part is shortest wavelength. Shortest wavelength. Okay, for shortest wavelength, in the Balmer series, he says Balmer series, n1, Balmer implies n1 2 second orbit and n2 3, 4, 5, etc. If I put n2 infinity is also called series limit, then resulting the wavelength is the smallest value. I write here 1 over lambda shortest. So r times 1 over n1 squared. What is the value of n1? n1 is 2 square minus n2 infinity square. 1 by infinity is 0. So 1 over lambda shortest. I write S for shortest. 1.097 10 to the power 7 R value. 1 by 4. So the lambda S, that is for shortest, 4 divided by, I found a reciprocal of this, 1.097 10 to the power 7. So the value of shortest wavelength lambda S, and it's coming around 3.6463. check it out in your calculator, minus 7 per meter. Use your calculator and find the value. It's coming around 3.6463 10 power minus 7 per meter. And second one, longest wavelength. For longest wavelength, n1 must be 2 for Balmer series, and n2 next value, that is 3. If you put 3, the wavelength will be longest, energy will be minimum, and frequency will be minimum. So the resulting wavelength in this case is longest, that is 1 by lambda L for longest, or times 1 by 2 square n1 minus 3 square. So value of R 1.097 10 to the power 7 into 1 by 4 minus 1 by 9. So the value of lambda L 1.097 10 to the power 7. Take LCM. 3 3 are 9. 36 is the LCM. So 9 minus 4, which is 5. You find the reciprocal value of this. So it is 36 divided by 1.097 10 raised to the power 7 into, okay, 10 raised to the power 7 into that 9 minus 4, 5. So the value is coming around 6.5633. Check it out with your calculator. Minus 7 meter is the longest wavelength of Balmer series. Shortest wavelength is 3.6463. You can write the answer in angstrom also. You shift by 4 places. 1, 2, 3, 4. So you get 3646.3 angstrom. If you write 3646, it becomes 10 power minus 10, which is 1 angstrom. And here also, longest wavelength, 6563.3, 10 power minus 10 angstrom. 6563.3 angstrom. Right? Children, we'll move on. The first member of Balmer series of hydrogen atom is 6563 angstrom. Right? 0 over A. Calculate the wavelength and frequency of second member of the same series. What he gives? He gives wavelength of first member, I denote by lambda 1, that is 6563 angstrom. And Rydberg constant is a constant, you can use that relation. You have to find second member's wavelength and frequency. First of all, you start like this. For first member, and the first point is hint. What you have to do? You have to use wavelength expression 1 by lambda 1 over n1 square minus 1 over n2 square. Wave number equation. Spectral series equation. Now, first member of which series? Balmer implies n1 2 and n2 next value, that is 3, 4, 5, etc. So n1 2, n2 3 is the first member of Balmer series. n1 2 implies Balmer. First member starts from series 3, second 4, third 5, and so on. Therefore, 1 by lambda 1, that equal to r times 1 over 2 squared minus 1 over 3 squared. The repeat of a previous problem. So 1 over 4 minus 1 over 9. And r times 9 4s are 36. 9 minus 4. So the value of lambda 1 r times 36, okay, lambda 1 by r times. You can write this. 1 by r times. I'll write this way. Right? 36 goes to numerator. Denominator 5 times r. Why? Because 9 minus 4 is 5. You may take it equation number 1. Actually, he wants, you know the value of lambda 1. Actually, he is not giving r in this example. Let us not use the value of r. So you will write for the second case. What it says, for second member of Balmer implies n1 2 and second member implies next value. First member 3, second member 4. So the wavelength of this series, second member, r times 1 over 2 square minus 1 over 4 squared. So r times 1 over 4 minus 1 over 16. So 1 by lambda 2 half, and LCM is 16. 4 4s are 16 minus 1. So numerator r times, can I remove this? R times 3 divided by 16. So the value of lambda 2. What is lambda 2? Lambda 2 is 16. You find the reciprocal of this, 3r. You may call it 2. Now you divide equation 2 by 1. You are not using the value of r straight away. You are removing it by dividing. Since he has given lambda 1, you can easily solve 16 by 3r. You can do it in mind. And 36 divided by 5r. 36 by 5r. So r cancels. How do you solve it further? You just write this way. Move it to the numerator. Numerator already 16, and this 5 comes to numerator into 5 into lambda 1 divided by 3 times 36. So the value of lambda 2, 16 into 5 into, what is lambda 1? Lambda 1 is 6563 angstrom. 6563 angstrom divided by 3 times 36. Anyway, you have calculator. You try it out using calculator. So the next is you have to find frequency. Maybe second part, frequency. What is frequency of radiation? According to wave theory, frequency F, or we denote by nu, that equal to speed of electromagnetic waves near a vacuum C divided by lambda 2. So lambda 2, for that case you have to find frequency. So what is C? 3 10 power 8. What's lambda? 4861.5 angstrom, 10 power minus 10. So the value divided by 3 is coming around the value nu as it is nu 0.00062 10 raised to power minus plus 18 plus 18 plus 10 plus 8. You shift by how many places? 4. So it is 6.2 10 to the power 4 power decreases, so it becomes 14 plus. Therefore, for the final value 6.2 10 to the power 14 SI unit hertz. Unit very important. That also carries a mark in the state board examinations. That's very, very important. Moving on, students, we'll see next one. Calculate the wavelength of H alpha line. You write it this way, H alpha. And also the Balmer series limit given R 1.097 10 to the power 7 per meter. Same value. See, the calculation part is same, very similar, same as the previous problem. Here, you understand this. What is H alpha line? H alpha line implies first member of Balmer series. Balmer series. You already done it. This implies Balmer implies N11 and first member implies N12. Next value 3. So we have done the calculation part. So refer. This implies refer problem 10. Problem 10. Problem 9. Problem 9. Same. Problem 9 you have to refer. And series limit. Series limit implies what? Again N12 for Balmer and series limit N to infinity. See, for series limit if you put N to infinity, wavelength will be minimum, frequency will be maximum. If you find frequency for this, it will be maximum than this. That also you need to know. For both the calculations, putting N12, N23. Second case N12, N to infinity. Refer previous problem, problem 9. Try on your own. Only difference is, instead of giving first member, that first member normally called by name H alpha line. Second member H beta. Third member H gamma. So H beta N1 2 N2 4 3 H alpha beta H H beta, that is N2 4. Okay. Next one, children. An electron transition occurs from n equal to 4 to n equal to 2 energy level in H atom. Find the wavelength of radiation if energy of the electron in the ground state is 13.6. This is 13 point, remove this. 13.6 eV. To which spectral series does it belong? Hint is very simple. We already done it. See, n equal to 4 to n equal to 2 implies what? Lower level second orbit, right? Higher level fourth orbit, right? That is, in our discussion, n1 2 and n2 4. If n1 into, what is your conclusion? n1 2 implies it is the second member of Balmer series. Previous problem, Balmer series. Second, why? N1 2, N2 3 first member, N1 2, N2 4 second member, and so on. And do the calculation part. Use 1 by lambda that equal to R into 1 by N1 square minus 1 by N2 square and solve. You try it. I leave here itself. You try. Okay. Yes. Now another one, slightly different. On giving energy to hydrogen atom, transition occurs from n equal to 1 to n equal to 4 if ionization potential of hydrogen is 13.6. What is ionization potential? Energy required to just emit an electron from first orbit to the infinite state outside the atom. Find energy absorbed in the transition and the wavelength of the emitted radiation if atom comes back to its original initial state. Solution. It's very easy. We all know what is the energy in nth orbit. Energy in nth orbit according to hydrogen atom theory proposed by Bohr is En minus 13.6 eV divided by n squared. If n1 1, then E1 minus 13.6 eV divided by 1, and this is what he says here in the datum. 13.6 eV is the energy required to just remove electron from first orbit to the outside the atom. That is this. Okay. If n1 4, put 4 here, minus 13.6 eV divided by 4 squared, and the value minus 0.85 eV. Therefore, what is change in energy? Energy absorbed during transition is nothing but difference in energy of the two states, that is delta E that equal to E2 minus E1. That's it. E2 minus E1. It's very simple. Yes. Minus 13.6. And this value, this difference, delta E that equal to minus 0.85 minus 13.6 values in EV, that's fine. 12.75 EV. This is the energy absorbed during transition. If the electron comes back, this first part of the calculation. The second part is, what is the frequency and wavelength? Frequency or wavelength, you can say. What is the wavelength of the radiation emitted, he says, when the electron comes back? for wavelength, since you know the states, energy states for wavelength, use same repeat calculation. 1 by lambda that equal to R into 1 by n1 square minus 1 by n2 square. Rest is same calculation. Put the values. Put n1 1 and n2 2, n2 4, sorry, n2 4. This belongs to Lyman series. Lyman series. In fact, third member of Lyman series. N11, N22 first member, N23 second member, N24 third member. Third member. This belongs to Lyman series. Remember? You solve this. Solve. I leave it to you. Use a calculator and solve. One more, children. Calculate the radius of the third orbit of H atom and energy in that orbit. It's very simple. A radius expression, we all familiar with this. Radius of any orbit Rn, epsilon naught n square h square by pi m z e square. Z1 for H atom, 1 for H atom. As it is H atom, Z1. And putting the values using values of constants, most of them universal constants, right? We get, I have a ready-made formula in my notes, you have referred it, right? Means putting the value of epsilon naught h pi m e, you will solve 0.53 angstrom into n squared for any orbit in general. If it is hydrogen like lithium, put 3. Helium, put 2 for Z, Z2 helium, Z3 lithium, and so on. But it's hydrogen, Z1, that ends the matter. Third orbit implies what? N that equal to 3. So R3, that is 0.53 angstrom into 3 squared. What is 3 squared? R3 that equal to 0.53 angstrom times 9. Right? So it's very simple calculation part. 4.77 angstrom is the answer. The rest, very simple, a repeat problem. Next. Energy, he wants you to find energy. What is energy in that orbit? Refer previous problem. What is energy in any nth orbit? Hydrogen minus 13.6 eV divided by n square. You put minus 13.6 divided by, what is n? N is 3 squared. So 13.6 divided by 9. The value comes around minus 1.51 EV, energy in EV. If you want it in joule, you multiply EV 1.6 10 power minus 19. Next is the energy of an excited hydrogen atom, minus 3.4 EV, minus 3.4 actually, minus 3.4 EV. Calculate the speed of revolution of the electron in that orbit. To find speed, what is the speed expression? Vn Ze square divided by 2 epsilon naught nh. Again, if Z1 H atom or H atom Z1, you think this way. Since it is H atom, you take Z1. Therefore, the value of Vn E square divided by 2 epsilon naught nh. Using the values of the constants, we can write 2.18 10 power 6 meter per second into 1 by n. So the thing is, you need to find the value of n. Once you find the value of n, answer is done. Next is energy in any nth orbit. Do you know? S. Just before this problem, we use that relation. Can you guess? Yes, that is En minus 13.6 EV divided by n square. Solve for n square. Minus 13.6 EV divided by what is En? En is minus 3.4 according to the problem. Minus 3.4 EV. You divide this. 13.6 divided by 3.4. So the value is coming around exactly 4. So the value of n root 4 to second orbit. Therefore the value of Vn, that is V second, 2.18 10 to the power 6 times 1 by n. In the place of n you are writing this relation, you are using this relation. See this. Now the value of velocity in the second orbit, you divide 2.18 by 2, 1.09 10 to the power 6 meter per second. See, as the electron moves to the outer orbits, the speed decreases, moves slower and slower. That's the conclusion. Okay, students, we'll discuss some more problems in the next video. Thank you.